conservation of energy.
In physics, the law of conservation of energy states that the total energy of an isolated system cannot change. It is said to be conserved over time. Energy can be neither created nor destroyed, but can change form. For instance, chemical energy can be converted to kinetic energy in the explosion of a stick of dynamite. A consequence of the law of conservation of energy is that a perpetual motion machine of the first kind cannot exist. That is to say, no system without an external energy supply can deliver an unlimited amount of energy to its surroundings.
History.
Ancient philosophers as far back as Thales of Miletus c. 550 BCE had inklings of the conservation of some underlying substance of which everything is made. However, there is no particular reason to identify this with what we know today as mass energy. For example, Thales thought it was water. Empedocles, 490-430 BCE, wrote that in his universal system, composed of four roots, earth, air, water, fire, nothing comes to be or perishes, but these elements suffer continual rearrangement. In 1638, Galileo published his analysis of several situations, including the celebrated interrupted pendulum, which can be described, in modern language, as conservatively converting potential energy to kinetic energy and back again. However, Galileo did not state the process in modern terms and again cannot be credited with a crucial insight. It was Gottfried Wilhelm Leibniz during 1676 to 1689 who first attempted a mathematical formulation of the kind of energy which is connected with motion, kinetic energy. Leibniz noticed that in many mechanical systems, of several masses, each with velocity v was conserved so long as the masses did not interact. He called this quantity the vis viva or living force of the system. The principle represents an accurate statement of the approximate conservation of kinetic energy in situations where there is no friction. Many physicists at that time held that the conservation of momentum, which holds even in systems with friction, as defined by the momentum, was the conserved vis viva. It was later shown that, under the proper conditions, both quantities are conserved simultaneously, such as in elastic collisions. It was largely engineers such as John Smeaton, Peter Awart, Karl Holtzmann, Gustav Adolf Hahn and Mark Seguin who objected that conservation of momentum alone was not adequate for practical calculation and made use of Leibniz's principle. The principle was also championed by some chemists such as William Hyde Wollaston. Academics such as John Playfair were quick to point out that kinetic energy is clearly not conserved. This is obvious to a modern analysis based on the second law of thermodynamics, but in the 18th and 19th centuries the fate of the lost energy was still unknown. Gradually it came to be suspected that the heat inevitably generated by motion under friction was another form of vis viva. In 1783, Antoine Lavoisier and Pierre-Simon Laplace reviewed the two competing theories of vis viva and caloric theory. Count Rumford's 1798 observations of heat generation during the boring of cannons added more weight to the view that mechanical motion could be converted into heat, and, as importantly, that the conversion was quantitative and could be predicted, allowing for a universal conversion constant between kinetic energy and heat. Vis viva then started to be known as energy, after the term was first used in that sense by Thomas Young in 1807. The recalibration of vis viva to, which can be understood as finding the exact value for the kinetic energy to work conversion constant, was largely the result of the work of Gaspard Gustave Coriolis and Jean-Victor Poncelet over the period 1819 to 1839. The former called the quantity quantité de travail, quantity of work, and the latter, travail mécanique, mechanical work, and both championed its use in engineering calculation. In a paper Überbedeutete der Wärme, published in the Zeitschrift für Physik in 1837, Carl Friedrich Muth gave one of the earliest general statements of the doctrine of the conservation of energy in the words, "Besides the 54 known chemical elements there is in the physical world one agent only, and this is called craft. It may appear, according to circumstances, as motion, chemical affinity, cohesion, electricity, light and magnetism. and from any one of these forms it can be transformed into any of the others.
Mechanical equivalent of heat.
A key stage in the development of the modern conservation principle was the demonstration of the mechanical equivalent of heat. The caloric theory maintained that heat could neither be created nor destroyed, whereas conservation of energy entails the contrary principle that heat and mechanical work are interchangeable. In 1798 Count Rumford, Benjamin Thompson, performed measurements of the frictional heat generated in boring cannons, and developed the idea that heat is a form of kinetic energy. His measurements refuted caloric theory, but were imprecise enough to leave room for doubt. The mechanical equivalence principle was first stated in its modern form by the German surgeon Julius Robert von Meyer in 1842. Meyer reached his conclusion on a voyage to the Dutch East Indies, where he found that his patients' blood was a deeper red because they were consuming less oxygen, and therefore less energy, to maintain their body temperature in the hotter climate. He discovered that heat and mechanical work were both forms of energy, and in 1845, after improving his knowledge of physics, he published a monograph that stated a quantitative relationship between them. Meanwhile, in 1843 James Prescott Joule independently discovered the mechanical equivalent in a series of experiments. In the most famous, now called the Joule apparatus, a descending weight attached to a string caused a paddle immersed in water to rotate. He showed that the gravitational potential energy lost by the weight in descending was equal to the internal energy gained by the water through friction with the paddle. Over the period 1840 to 1843, similar work was carried out by engineer Ludwig A. Kolding, though it was little known outside his native Denmark. Both Joule's and Meyer's work suffered from resistance and neglect, but it was Joule's that eventually drew the wider recognition. In 1844, William Robert Grove postulated a relationship between mechanics, heat, light, electricity and magnetism by treating them all as manifestations of a single force, energy in modern terms. In 1874 Grove published his theories in his book The Correlation of Physical Forces. In 1847, drawing on the earlier work of Joule, Sadi Carnot and Emil Clapeyron, Hermann von Helmholtz arrived at conclusions similar to Grove's and published his theories in his book Über die Erhaltung der Kraft, on the conservation of force, 1847. The general modern acceptance of the principle stems from this publication. In 1850, William Rankine first used the phrase the law of the conservation of energy for the principle. In 1877, Peter Guthrie Tayet claimed that the principle originated with Sir Isaac Newton, based on a creative reading of Propositions 40 and 41 of the Philosophiae Naturalis Principia Mathematica. This is now regarded as an example of Whig history.
Mass-energy equivalence.
Matter is composed of such things as atoms, electrons, neutrons, and protons. It has intrinsic or rest mass. In the limited range of recognized experience of the 19th century, it was found that such rest mass is conserved. Einstein's 1905 theory of special relativity showed that it corresponds to an equivalent amount of rest energy. This means that it can be converted to or from equivalent amounts of other, non-material, forms of energy, for example kinetic energy, potential energy, and electromagnetic radiant energy. When this happens, as recognized in 20th century experience, rest mass is not conserved, unlike the total mass or total energy. All forms of energy contribute to the total mass and total energy. For example, an electron and a positron each have rest mass. They can perish together, converting their combined rest energy into photons having electromagnetic radiant energy, but no rest mass. If this occurs within an isolated system that does not release the photons or their energy into the external surroundings, then neither the total mass nor the total energy of the system will change. The produced electromagnetic radiant energy contributes just as much to the inertia, and to any weight, of the system as did the rest mass of the electron and positron before their demise. Conversely, non-material forms of energy can perish into matter, which has rest mass. Thus, conservation of energy, total, including material or rest energy, and conservation of mass, total, not just rest, each still holds as an equivalent law. In the 19th century these had appeared as two seemingly distinct laws.
Conservation of energy and beta decay.
The discovery in 1911 that electrons emitted in beta decay have a continuous rather than a discrete spectrum appeared to contradict conservation of energy, under the then current assumption that beta decay is the simple emission of an electron from a nucleus. This problem was eventually resolved in 1933 by Enrico Fermi, who proposed the correct description of beta decay as the emission of both an electron and a non-entire neutrino, which carries away the apparently missing energy.
First law of thermodynamics.
For a closed thermodynamic system, the first law of thermodynamics may be stated as: whereas the amount of energy added to the system by a heating process, is the amount of energy lost by the system due to work done by the system on its surroundings and is the change in the internal energy of the system. The D's before the heat and work terms are used to indicate that they describe an increment of energy which is to be interpreted somewhat differently than the increment of internal energy, see inexact differential. Work and heat refer to kinds of process which add or subtract energy to or from a system, while the internal energy is a property of a particular state of the system when it is in unchanging thermodynamic equilibrium. Thus the term heat energy means that amount of energy added as the result of heating rather than referring to a particular form of energy. Likewise, the term work energy means that amount of energy lost as the result of work. Thus one can state the amount of internal energy possessed by a thermodynamic system that one knows is presently in a given state, but one cannot tell, just from knowledge of the given present state, how much energy has in the past flowed into or out of the system as a result of its being heated or cooled, nor as the result of work being performed on or by the system. Entropy is a function of the state of a system which tells of the possibility of conversion of heat into work. For a simple compressible system, the work performed by the system may be written. Whereas the pressure and is a small change in the volume of the system, each of which are system variables. The heat energy may be written. Whereas the temperature and is a small change in the entropy of the system. Temperature and entropy are variables of state of a system. For a simple open system, in which mass may be exchanged with the environment, containing a single type of particle, the first law is written. Whereas the added mass and is the internal energy per unit mass of the added mass. The addition of mass may be accompanied by a volume change which is not associated with work. For example, for a liquid-vapor system, the volume of the vapor system may increase due to volume lost by the evaporating liquid. In the reversible case, the work will be given by where V is the specific volume of the added mass.
Noether's theorem.
The conservation of energy is a common feature in many physical theories. From a mathematical point of view it is understood as a consequence of Noether's theorem, which states every continuous symmetry of a physical theory has an associated conserved quantity. If the theory's symmetry is time invariance, then the conserved quantity is called energy. The energy conservation law is a consequence of the shift symmetry of time. Energy conservation is implied by the empirical fact that the laws of physics do not change with time itself. Philosophically this can be stated as nothing depends on time per se. In other words, if the physical system is invariant under the continuous symmetry of time translation, then its energy, which is canonical conjugate quantity to time, is conserved. Conversely, systems which are not invariant under shifts in time, an example, systems with time-dependent potential energy, do not exhibit conservation of energy, unless we consider them to exchange energy with another external system so that the theory of the enlarged system becomes time invariant again. Since any time-varying system can be embedded within a larger time-invariant system, with the exception of the universe, conservation can always be recovered by a suitable redefinition of what energy is and extending the scope of your system. Conservation of energy for finite systems is valid in such physical theories as special relativity and quantum theory, including QED, in the flat spacetime.
Relativity.
With the discovery of special relativity by Albert Einstein, energy was proposed to be one component of an energy momentum 4 vector. Each of the four components, one of energy and three of momentum, of this vector is separately conserved across time, in any closed system, as seen from any given inertial reference frame. Also conserved is the vector length, Minkowski norm, which is the rest mass for single particles, and the invariant mass for systems of particles, where momenta and energy are separately summed before the length is calculated. See the article on invariant mass. The relativistic energy of a single massive particle contains a term related to its rest mass in addition to its kinetic energy of motion. In the limit of zero kinetic energy, or equivalently in the rest frame, of a massive particle, or else in the center of momentum frame for objects or systems which retain kinetic energy, the total energy of particle or object, including internal kinetic energy and systems, is related to its rest mass or its invariant mass via the famous equation. Thus, the rule of conservation of energy over time in special relativity continues to hold, so long as the reference frame of the observer is unchanged. This applies to the total energy of systems, although different observers disagree as to the energy value. Also conserved, and invariant to all observers, is the invariant mass, which is the minimal system mass and energy that can be seen by any observer, and which is defined by the energy-momentum relation. In general relativity, conservation of energy momentum is expressed with the aid of a stress-energy momentum pseudotensor. The theory of general relativity leaves open the question of whether there is a conservation of energy for the entire universe.
Quantum theory.
In quantum mechanics, energy of a quantum system is described by a self-adjoint, or Hermitian, operator called the Hamiltonian, which acts on the Hilbert space, or a space of wave functions, of the system. If the Hamiltonian is a time-independent operator, emergence probability of the measurement result does not change in time over the evolution of the system. Thus the expectation value of energy is also time-independent. The local energy conservation in quantum field theory is ensured by the quantum-Noether's theorem for energy momentum tensor operator. Note that due to the lack of the universal time operator in quantum theory, the uncertainty relations for time and energy are not fundamental in contrast to the position momentum uncertainty principle, and merely holds in specific cases. See uncertainty principle. Energy at each fixed time can be precisely measured in principle without any problem caused by the time-energy uncertainty relations. Thus the conservation of energy in time is a well-defined concept even in quantum mechanics.